Hey everybody, my name is Emerson Kirby and I work with the United States Department of Agriculture's Natural Resource Conservation Service. And today I'm going to be talking to you all about soils for the area Envirothon. This presentation was put together a few years ago by Janine Fryman, our soil resource scientist. She is now since retired, so I'm going to be using her presentation to talk to you guys a little bit about soils and what we can do with them and what they can do for us. Some of the slides are going to be a little dated, and some of the slides also aren't going to be particularly useful to you all, so I will skip over some of them, but the wonders of this being recorded, you all can pause and go back and look at stuff. And I will also try to include a copy of this PowerPoint with the video submission so that you all can use it, because it does have some links embedded in it that I think might be beneficial for you all as well. So without further ado, let's go ahead and get started talking about soils. So some of the topics I'm going to cover briefly: NRCS's role in soil resources, a general overview of the soil resource and soil science, and soil quality for homeowners and gardeners. And this could also be applied to someone doing row crops or any type of crop, really. We'll touch on soil testing and a few things like that. That has a pretty broad reach, a broad spectrum that isn't necessarily tied to homeowners, gardeners, and those in urban settings. But it's still valid information. So with soil, a quote by Aldo Leopold: "We abuse land because we regard it as a commodity that belongs to us. When we see land as a community to which we belong, we may begin to use it with love and respect." So that is a pretty profound quote from Mr. Leopold. Hugh Hammond Bennett, he is what we consider the father of modern soil conservation in the United States. And I'll let you guys read over this. But something that he did that was very important: he was going to give a speech before Congress on the effects of the Dust Bowl and why conservation was important. And he timed his speech to Congress in such a way that he knew a dust storm was blowing in from the west, and he knew about what time it was going to hit Washington, D.C. So while he was giving his speech to Congress, the sky grew dark. Everybody went outside to see what was going on, and they could see this giant dust cloud enveloping Washington, D.C., and that was all soil that had blown out of the Midwest. So he had a pretty good hands-on demonstration and example for the members of Congress that he was speaking to, and that is why we call him the father of soil conservation in the United States, because he helped get everything started with us as conservationists. You can briefly see our mission here, and our vision: harmony between people and the land, helping people help the land. Here you can see our vision and mission, and we're also partners with the soil and water conservation districts across the state of Virginia. We are present in all 50 states and territories. So soil quality, some of the vital functions that soils provide us with or do for us: they sustain plant and animal life, both below and above the surface. They regulate and partition water and solute flow through the environment. You can kind of see the diagram to the right with rain. Some of that rain will infiltrate the soil and some of it will run off, carrying things with it like soil and other nutrients. As well as when it infiltrates, it can move nutrients from upper areas of the soil profile to lower areas of the soil profile. Soils also are good at filtering, buffering, degrading, immobilizing, and detoxifying things that may get into the soil that may be brought in through rain or deposited by air deposition or people bringing stuff in, animals, things like that. Soil is a really good filter, and it also can help trap and break down things, or at least keep things from moving further down into the soil profile, protecting the groundwater aquifers and things like that. And over time, it can actually help break down, degrade, and detoxify certain chemicals, giving those chemicals time to break down on their own or to allow biological processes with plants and or other animals, microorganisms, to break those down further. Soil is also really good at storing and cycling nutrients. We have the carbon cycle, the phosphorus cycle, the nitrogen cycle. There are several other cycles with how nutrients move through the environment. They all are very important. Nitrogen, potassium, and phosphorus are the three main macronutrients for all plant life. And that is going to be one of the main things that we see being used in agricultural fields and on farms and things like that, with producers applying NPK in various rates to meet the needs of the crop that they are growing. And then soil also provides support to structures, our houses, bridges, other infrastructure like telephone lines, electrical power grids, things like that. You want good solid soils to build on. Some soils are suitable for building, other soils are not. So it's important to know kind of what type of soil we're working with when planning certain projects. And then here is Hugh Hayman Bennett and W.C. Loudermilk, a quote from them. I'll let you all read over that. But basically, the rise and fall of civilizations, kingdoms, countries, nations, things like that can be tied to how those people treated their soils and the productivity of their land. And then we have these things called soil surveys, and each county in Virginia should have its own soil survey. You can find them online or in print in a hard copy book. They are rather lengthy. And what it is going to do is it is going to have the county broken down into areas. And then in those areas, we are going to see the different soils that have been mapped in that area. And I've got some better pictures and stuff coming up, but I just wanted to give you guys a little overview of the soil survey. And then there are unique physical and chemical, also biological properties from soils, and it's important to their use. And then those soil properties are going to be either inherent or dynamic, and we'll go over those two definitions here in a little bit. But when you're looking at a soil, you're going to try to note, as many things as you can about that soil just with your eyes, with your nose to smell them, and then being able to feel them. So you're going to pay attention to things like the color. Is the soil a uniform color from the top going on down? Are there different layers or bands of colors? Are some layers darker or lighter than others? It really just depends on where you're at in the landscape, what you might find. So you want to note the different colors that you see. Also, you want to look at texture. Is the soil gritty? Does it feel like it has a lot of sand in it? Does it feel like it has silt in it? Is it kind of tacky? Or does the soil clump up and stick to itself like it might have a lot of clay in it? That's something that you want to look at to see what the texture of that soil might be. And keep in mind, each layer in that soil may have a different texture. You're going to look at the structure, and we'll cover structure here in a little bit as well, on the way the soil looks when you dig down into it. Consistency, kind of look and see what the soil looks like. Is it consistent? Are there little variations? In this picture here, you can see where the roots have gone down and brought oxygen down into the soil layer where those roots have died and broken down, leaving organic matter. So you start to see some brown streaks down into the soil. That ties into roots. You want to see when you dig down if you see roots. Some soils are easy for roots to penetrate and dig down, so you may get very long fibrous roots. Other soils may have what we call a hard pan or a fragipan, in which you go down a certain depth and you hit a very hard root restrictive layer, typically as a result of plowing over and over again, that it may be very difficult for those roots to penetrate deeper into the soil. You can also look at pores and porosity. There are micropores and there are macropores. Macropores tend to come from things like living organisms, roots, earthworms burrowing, groundhogs, invertebrates, things like that that burrow down into the soil. And then there are some other features that we'll look at as well. Um, and then here's a little thing at the bottom. For soil is a natural body of solids, liquids, and gases with either horizons or layers or the ability to support rooted plants. And then the study of soil is called pedology. We've got a few more definitions for soil coming up here in a little bit as well. So there are 23,000 soil series in various combinations with different slopes and surface textures across the United States. And these are all going to be influenced by five main soil forming factors. And that's going to be parent material. That is going to be the material, the rock that forms these soils over time. Climate, if you Soils form faster in warm, wet areas like the tropics. They're going to form slower in colder, drier places or where it tends to stay frozen more, like in the North and South Pole. Living organisms, they're going to impact what goes on with that. So if you're in a warm tropical climate, you're typically going to have a lot of soil biotic activity, a lot of microbes, some macro and microinvertebrates, as well as other organisms interworking with that soil. Whereas if you go up north, you're not going to have as many biologic factors impacting the rock or the soil there, so it's going to take longer for it to form. And then we can look at topography. And topography, if you're on top of a mountain, the soil most likely will be shallower than at the bottom because when it rains, if the soil is not protected, it's going to get washed downhill. Also, gravity will help pull things down over time. So you're going to have thicker slope or thicker soils at the bottom slope of a mountain as compared to the top of a mountain, given topography. And then time. The longer something's been exposed to the weathering factors and the other like living organisms or climate, typically the better well developed those soils are going to be. If it's newly exposed bedrock, you would expect that it hasn't had a lot of time to have those other factors interfere with it. So you wouldn't expect to see a well developed soil there or even maybe a developed soil, just depending. So here's a couple different definitions of soil. The one at the bottom is the one that I like best, the taxonomic definition, saying that it is a collection of natural bodies occupying portions of the Earth's surface that support plants and that have properties due to the integrated effect of climate and living matter acting upon parent material as conditioned by relief over periods of time. And this definition here kind of captures the previous soil forming factors that we talked about on this slide here. I'll give you a few seconds to either read over these definitions or pause it and read over it, and I will change the slide. And then we have different scientific names for these soils. Like plants and animals, we classify soils. As humans, we like to classify everything into groups. It makes it easier for us to study and understand things and break things out and group them. Certain soils that might have a relatively sandy texture we can group over here, and then soils that have maybe a lot of interaction with the high water table or water, we may put into another group. So you can kind of read here at the bottom the different soil orders that we have, and then the formative terms where that came from. And that gives you an idea or a hint as to what to expect with those soils or how they formed. Web Soil Survey is something that we use as an online source for soil surveys, but the print soil surveys that we were talking about earlier, they look like this. This is from Washington, Pierce County in Washington. A soil survey is going to include maps, descriptions of the soils, the landscape, the profiles, properties of those soils, the climate in which those soils formed, what the current climate is out there, and interpretations of these soils by those who did the sampling. And these are excellent sources of information. A lot of times, before going out in the field, we can look at a soil survey and get an idea of what to expect on that farm when we go out there, where we could maybe find the cropland versus timberland and things like that, as well as if a landowner buys a farm or buys a piece of land and wants to know what they can do with it or where the best areas to crop and stuff are, we can show them a soil survey, and the properties of those soils might help dictate where they, crop corn or soybeans, or where they graze pasture for cattle or cut hay or just leave it into timber. About 3,000 counties in the United States have a soil survey. Here in Southwest Virginia, all of our counties have a soil survey. And then limitations with the soil that we have to understand, concerns for life and properties. I'm going to quickly go over a few of these with you all. And these are things that we want to consider when building on soils or constructing with soils or even just farming these soils. Allergies, there could be allergens in the soil. There could be soil that is corrosive, and that could be like an acidic soil. where you want to put a concrete sidewalk or something like that, and you have an acidic soil that's going to interact with that concrete, which is alkaline, so it can eat the concrete. It can also eat metal, degrade metal. And then you also have like a corrosive soil with like a lot of acidic materials in it with iron dissolved in it. And when water flows over this concrete with this iron in it in the acidic solution, the iron will actually precipitate out as it reacts with the alkaline concrete, staining the concrete orange. So it causes some aesthetic issues as well. Dust, you want to see, you may be working somewhere where the soil easily dries out and it easily dislocates from the other soil particles around it and is easily transported by the wind. We can look at flooding. How often is a soil flooded? If the soil is frequently flooded or deals with a lot of ponding and stuff like that, it might not be a great place to build a house. It also might not be a great place to put any cropland for any cash crops or commodities. It might be something best to stay in like a riparian area, stay in a forested area, and just left alone. It may be harder to actually make that land productive and cost more than what it would ever pay back out in products. Gypsum dissolution, that's going to be if you have like an alkaline soil. We've got piping, we've got rapid runoff. So if you have like a compacted soil on a very steep slope, or if you have a very shallow soil that is mostly rocky, or it's the depth bedrock is very shallow, you may have a lot of rapid runoff in high rain events, and that soil won't be able to hold or absorb a lot of that water, and that water is just going to run off. So if you put down fertilizer or something like that and it rains, it potentially will wash that fertilizer away before plants have a chance to use it. So you're wasting your money there. We've got sand blowing, septic failure, sinkholes. Here in Southwest Virginia, our parent material is going to be a lot of sedimentary rock. Limestone is the big one with sinkholes, and that's going to be when you have acidic water, acid rain, things like that, dissolving caves and holes underneath the soil profile, underneath the soil surface, and you end up with sinkholes. And these sinkholes are direct conduits to groundwater. So if you have something that might be polluting on the surface near a sinkhole, and it rains and washes that stuff into a sinkhole, whatever those contaminants are will most likely end up in someone's drinking water, because we also have a lot of wells around here that people get their drinking water from, as well as to irrigate crops and drinking water for livestock. Soil-borne diseases. A lot of places on the old cattle trails out west still have anthrax in the soil, and that is just an effect of them traveling back and forth over the years with so many head of cattle that those diseases just stay in the soil, and it takes a while for them to die out. We've got sulfidic materials, water tables. If you have a seasonally high water table or a perched water table, depth to water might be anywhere from 6 to 12 inches. So when you dig down into that soil, you're going to hit water pretty easily. So that might make putting fencing in difficult, as the fence may rot faster due to the water, as well as planting certain crops that have deep root systems. When they get into that water, the water table, they may actually die because they kind of drown because they get so far down, and then they hit this water laden label and suffocate, or they're not able to properly uptake nutrients, and they die. And there are other contaminants that might be in the soil. Those could be naturally occurring contaminants, things that we don't want there, as well as contaminants deposited by people. And that could be something like on mine reclamation, where we have acid mine drainage and things like that that could affect the soil. We have crop loss, and that could be due to various factors. We have erosion. That's going to be the loss of your topsoil, and even in some cases subsoil, because in some places we have lost all of our topsoil and we are actually farming subsoil. Then there's the frost action. If you're in an area where it freezes, the soil, when it's wet, can heave and expand when the water freezes in the soil. So that can cause foundations to crack. It can cause fences to shift a little bit with the posts and stuff. So that's something you want to look at. Liquefaction. The best example I can give you all is to think of like an earthquake, and you are sitting on top of a soil that might be kind of sandy with some water in it. And think of quicksand in the sense that as the earth begins to shake and vibrate, the sand, the soil kind of liquefies, and you can actually have structures, foundations, and things like that sink into the ground a little bit and start to buckle and crack. Radon, that is a radioactive gas that comes from the breakdown of uranium. There's quite a bit of radon in pockets here in Southwest Virginia. It is carcinogenic. If you breathe a lot of it in, it can affect your lungs and lead to lung cancer. Salt buildup in soils, that can be natural as well. That can also be from applying excess fertilizers and things like that without the proper amount of water, rainfall, irrigation, something like that to help flush those salts out of the soil. Sedimentation, if you're in an area that floods a lot, that floodplain will experience sedimentation, that as the floodwaters recede, they will deposit sand, silt, and clay. So if you are in a certain area where you're growing a crop that you need nice clean leaves, like lettuce or something like that, and it floods on it, you're going to get your leaves all dirty and contaminated with whatever in that water, and chances are you wouldn't be able to sell that because it's going to be contaminated. Shrink swell, that's something with a lot of clays. People in Texas and other places that have a lot of shrink swell clays, you'll actually see people watering the foundations of their house during a drought. And that's because they're trying to keep the clay nice and hydrated. Because if that clay shrinks and dries out, and then it rains again and it expands, the foundations of these houses and buildings can shift because the clay is going to shrink when it dries out and then swell and expand when it gets wet. Slope failures and subsidence, that's when you might have a lot of rain in an area and the soil's trying to hold on to it and it just can't, and you get a failure or you get some subsidence along a creek or something like that. And then urban hydrology, and we'll talk about urban hydrology towards the end of the presentation, I believe. But just a quick thing, you can see this picture here with these cars flooded. A lot of our urban areas are covered with what we call impervious surfaces. That's going to be roads, parking lots, buildings, sidewalks, and things like that, that aren't going to let the water that hits them infiltrate into the soil. Instead, they are going to intercept this water over large areas and consolidate it into smaller areas, shooting it into streams and creeks, which will lead to localized flash flooding. So that's something to keep in mind as well. We're starting to move to places putting in a lot of rain gardens in parking lots and places like that to allow the water to dissipate and slowly sink down into the ground. Here's Web Soil Survey. It's an online tool. I encourage you all to look at it and use it. You just can type in Web Soil Survey in a Google search. You're going to push this green button up here that says Start Web Soil Survey. You can zoom into an area of interest, or you can type in an address, and it will take you there, and then you can play around with it, and it will tell you all sorts of things about that soil. There are a lot of tabs that will be on the left-hand side of the screen. You can look at floodplain maps if it's in a floodplain. You can look at all sorts of information related to that soil without ever having to step foot on that farm, on that tractor piece of land. It's a really good resource to kind of arm yourself with some knowledge before ever going out in the field so that you have an idea of what to expect when you get there. It's also available as an app on your phone, so you can download it and use it there while you're in the field as well. And this is an example of an area of interest drawn in Web Soil Survey. It's in Blacksburg, Virginia. You can see the different soil series that they have listed throughout the community. It's going to be a number followed by a letter, and then W, you can see down here, this is water, this is the duck pond, right here's the drill field. So you can kind of see how they've got it broken down into the different soils, and that's going to be different parts of the landscape, closer to water, away from water, steep slopes, gentle slopes. Each one of these numbers and letters is going to correlate to a soil type that you can go back and look in the soil survey and get additional information from, or you can get that information from Web Soil Survey. Here's just another image of Montgomery County looking down at the different soils that they have mapped in this area to the south of this map. And then soils orders, there are 12 orders of soil taxonomy, and again, each of them has its own definition of like what to expect and how they formed or where you would expect to find them in the landscape. Here's a map of global soil regions. You can kind of see how they're spread out across the world. You can kind of see where desert regions are versus where the Arctic pole regions are, the colder areas. You can see where our tropics are. It's a very beneficial thing to look at as well. This is a little bit of a dated map from 1997, but it's land capability class by state, and it's got it broken down into class 1, 2, 3, 4, 5, and I believe 6 and 7, maybe even 8. And you can read the classes. I know it's a little blurry down there, but it will help you understand, what you can do in each state, or what amount of soil for each classes in each state. And then some local soils here in Southwest Virginia. So the geologic provinces in Virginia, Erosion Valley, Blue Ridge, Cumberland Plateau. That's where I'm at. And then we've got the Piedmont and the Coastal Plain. And this is just a soil survey example from Washington County, Virginia, near Bristol. And this is just kind of what to expect when you're looking at a soil survey. It's got some different elevations on it, and then what to kind of expect as you're going through the area. And then here is another area for the relation to landforms in the Ridge Valley. And you can see we've got a cave down here, some karst area in this limestone bedrock. We've got our Frederick soil on top. That's one of the soils that we have most of around here that I work with anyways. You can see some Watahala soils as well. You can see alluvium and colluvium as the water comes down through here. We see our toe slope and foot slope. And you can see we're a little bit flatter to the west and a little hillier to the east of this image. And then we see the stream coming down through the valley. We see the alluvial deposits. We see some colluvial deposits as well. And then we've got some residuum, and we'll go into a little bit of detail on one of these later slides. So here again, we see a floodplain going from side to side, and it's kind of got it denoted up there at the top with the arrows. And you see the stream, the Holston River, coming down through. You see recent alluvial deposits where the stream is, and then old alluvial deposits or water-based deposits where the old floodplain may have been, or where the stream has meandered back and forth. So you can see all these different components of the landscape. So there's going to be different soils in each area, and each soil is going to have its own unique properties and its own age and stuff based on how long it's been developed. Like this recent alluvium may not have a lot of structure to it, but the older alluvium may have a little more structure to it as it's been exposed to the elements and time, organisms and stuff like that, to begin forming some nice horizons or layers. Here is a soil survey from Russell County, Virginia. You're starting in the west with the mountains, and you work your way down to a creek on the eastern side of this. And you can see there are different things. Typically, we have our limestone valleys and sandstone ridges. Limestone is more susceptible to erosion from water, especially acidic water. And then sandstone is a little more resistant to weathering from water, so the ridges tend to be capped in sandstone, but then the valleys, the valley floor, tend to be made out of limestone and some other easily dissolved sedimentary rocks. And here's just another example with the Clinch River and how you can expect to see certain things in the landscape. And then this is something that you find in areas like Buchanan County, Dickinson, Wise, parts of Russell, and parts of Tazewell County. But it's an area that was strip mined. So this soil has been classified as disturbed and does not have any natural soil properties. What we did is there was soil there was a mountain there, and we removed all of that to access the coal underneath and then tried to put it back together, trying to shape the mountain back to the way it was, and come back in a couple of thousand years, maybe a million years, and we might start seeing some good soil formation with the onset of some layers, get some plants on there, gets to hold what little soil might be there in place, and then get them to start bringing nutrients up from the lower depths of those rock piles, gravel piles, and then get some organic matter in there from some leaves and stuff and some other organisms, and then we'll start working on forming a soil. Given our climate, it might take a little while. It'll take longer than in the tropics, but we have a pretty decent climate around here, so give it a couple thousand years or so, and we might start getting some good soil back on these slopes. Here's just an example of looking at a soil profile from a soil pit view. You can see a couple different horizons or layers in there. At the top, we have the dark brown layer, and then it looks like we have from here to here-ish with our dark brown layer, about 12 inches or so. And then, without being out in the field and looking at it, just looking at this picture, it looks like we have a little bit of a distinct layer from right here to maybe right in here. It's a little bit lighter. And then from here to here, we get a little bit lighter. And then from here to here, we get lighter. And you can also see what looks like a rock poking out there. And then you can read the description down here at the bottom, in which the soil is about 54 inches deep. The subsoil is generally strong brown, sandy clay loam. Depth to bedrock is more than 60 inches. So it looks like we're starting to get into some rock here, but if we went further down in the profile, we would actually start getting into some bedrock. Here's an example of something from Grayson County. You can see the description at the bottom where it says the average content of semi-rounded rock fragments is as much as 35% in the solum and as much as 60% in the substratum. The depth to bedrock is more than 60 inches. So even though we're hitting a lot of rock, these are loose rocks. They're not considered bedrock. It's not solid. But we have like a thinner looking soil from here to about right here. And then from here down, we get into a different looking layer. Again, without being out in the field and looking at this, it's kind of hard to tell, but it looks like there's kind of two distinct layers there. And then as we go further down, we get into more rock. And then here's from Rockbridge County. Again, if you read the bottom, it's got an argillic horizon that begins directly below the topsoil and extends below the depth of 60 inches. So we've got a topsoil layer that looks like it's going from here to somewhere around here, depending on which way we look. And then from here down is going to be the argillic horizon. That's going to go all the way down into the soil profile. And then here we have a soil that is on like a 0 to 3% slope. It's rarely flooded by bodies of water, but they pond occasionally throughout the year, and they do support hydrophytic vegetation. And because it's just so flat out there, like in the coastal plain or some of these other areas where it's flat, when it rains, the water just does not have anywhere to go. It doesn't have anywhere to flow off the landscape. And once those soils get saturated and stuff, there's nowhere for the water to go there as well. So then the water just typically ponds on top, and that can lead to some hydrophytic vegetation. And that's just vegetation that is water loving. It likes water, it likes wet roots, stuff like that. These pictures are hard to kind of tell what's going on here, but it's just an example of when we take a soil auger out and dig a soil pit with it and then try to analyze what the soil qualities profile layers may be there. Fun fact, the Pamunkey soil is the Virginia state soil, and I believe Pamunkey soil holds the world record for largest harvest of both corn and soybeans. And then some fundamental concepts of soil. We have inherent or static properties. Inherent properties are going to be static properties, soil properties that do not change. And then dynamic properties are properties that are changed by management and treatment over time. And then here's just an example of soil horizons and then some pedons. So again, we have the 5 soil forming factors, which are parent material, climate, living organisms, topography, and time. And then up here in the upper left, we have what we call a soil pedon. And a pedon is going to be a subsample from a polypedon, which is a group of many pedons. And that polypedon is going to be a subsection of a landscape. And that's coming from the diagram on the right. But not every soil is going to have these exact layers in this exact order. This is just a typical example. You have your O horizon, which is going to be like your organic matter, your organic material, your A horizon, your B, maybe some clays, and then your C, which may be getting into some rock before you get down to your bedrock. Not every soil is going to have these, and there are some soils that may have a few different layers, like an E layer, which would be an eluviated layer, which typically would be somewhere in between like this A and B, and it would be a white colored layer in which all of the minerals and stuff have been leached and removed from that layer and translocated down into the this like B layer below it. And you may also get some layers that have components of 2 different layers, so you may call it like a BC or a CR. some different layers like that. So soil, an example of the component definition of soil being a mixture of minerals, organic matter, water, and air, is 45% mineral matter, 25% both of air and water, and then 5% of organic matter. And here we have examples of the three particle sizes of soil, or the three things that make up soil. We have sand, silt, and clay. Sand is going to be your largest particle. Silt is your second largest, and then clay is going to be your smallest. Now, sand is very easy to dislocate. It's very easy to remove from other grains of sand. They're not tightly bound together. Sand is not tightly bound to the soil. So it is easily removed, but it is very hard to transport because it is so heavy. So when you get flooding or erosion and stuff like that, the sand may get dislodged first, but it may not travel as far. Whereas something like clay, where it's so small, it's very hard to dislocate from other components of the soil, because clay is its electrical charge. It is very sticky to itself and other things, so it's very hard for clay to get dislodged from other stuff. But once clay is dislodged, where it is so light and so small, it is easily transported by water very long distances before settling out of the solution. And something you can do to kind of get an idea of how much sand, silt, or clay might be in a soil sample is you can put it into a mason jar with water and shake it up and let everything settle out. Your smaller rocks and sand will fall out first, followed by your silt, and then after a day or two, you'll have your clay start to precipitate out as well. And you can kind of get a rough idea on the percent of each of those minerals in your soil. Again, here's the soil forming factors on a landscape. You can get an idea of where you might have well-developed, weakly developed, and moderately developed soils. So you've got some well-developed soil up here on this side slope, up on top of this hill. You've got your bedrock, your soil parent material. You've got a well-developed soil down to 60 inches. You've got several different layers before you get down to the bedrock. This moderately developed soil, you see it's a little further away. It might be made out of some old alluvium, and you've got some bedrock here, so you're starting to get a little bit of development in that soil profile. And then this weakly developed soil, it says it came from recent alluvium, so that's going to be something that was deposited pretty recently. So you wouldn't expect to have a lot of development in that soil. So your younger soils typically will be maybe in your floodplains if you have a landscape like this, whereas some of your older soils will be in your upland areas and outside the floodplain, or in some of the older floodplains from that body of water. All right, and with soils, we have additions. That's going to be something like fertilizer, maybe grass clippings, animal manure, even dead organisms. We have losses. That's going to be things that are removed from the soil. That can be through something like erosion, where you lose soil that has nutrients attached to it. You could also have losses in the sense of harvesting crops. You're putting nutrients in the soil, those plants are taking the nutrients up, and then you're removing those plants, those crops with those nutrients, taking them away from that soil forever. So you'll have to come back with more additions if you wanted to crop it continuously, or continue cropping it and getting the same yield. We have translocations, and that's just going to be moving things like additions down into the soil, or even up from the bottom of the soil through something like plant roots, digging down and then pulling things up. We have losses also in the sense of leaching, in which water carries dissolved nutrients and minerals further down into the soil profile. And then we have transformations, in which something may change from one elemental group to another. And if you really want to know more about that or something, you can study the nitrogen cycle. That is a great example of transformations in soil, and I wish I had a slide for that. But pay attention to the nitrogen cycle. It will show you different additions, losses, and transformations of nitrogen in the soil, from nitrate to nitrite, organic and inorganic nitrogen, and then it also just sublimes into the air as well. So some physical properties of soil: we have soil texture, structure, color, and then the bulk density of the soil. And this is all going to be beneficial in understanding what we can maybe grow on this field or what we might be able to build on this field based on what some of the physical properties of the soil are. And we have a USDA textural triangle here, and it will help you figure out what type of soil you're dealing with respect to percent sand, silt, and clay. And I believe we've got an example here. So what you do is you find the percent sand, silt, or clay, and you will follow the respective lines until they all cross in one spot, and then that would be what you would have. This one is an example of a silt loam. Um, you're going to have whatever your total is equal 100%. So you might have 30% sand, 30% clay, 30% silt, and wherever that takes you, following the lines will be what that is. So that's how you use the USDA textural triangle. Clay and sand are probably going to be the easiest ones for you to figure out just by looking and feeling the sand, and then you can kind of deduce what the silt's going to be, because if you already know what the clay and the sand are, you would just subtract that from 100%, and that would give you what your silt would be. Some soil structure examples, we have granular, and you can just imagine kind of like on a macro scale, just looking at a handful of sand. You can see how it's all just kind of loosely clumped up there together. We have platy, and that you can see is everything is just kind of smushed together in layers. You don't see a lot of big gaps in between the layers for things like water or air to move through. You've got wedge. We have blocky, and in blocky we have subangular blocky, and that's going to be kind of like a more rounded blocky structure. And then we have angular, and that's going to have some sharp points and angles on it. Then we have prismatic and columnar. And aspects of soil structure: the arrangement into aggregates of desirable shape and size, the stability of those aggregates, and then the configuration of the pores are some things that we want to look at with respect to soil structure. And then also soil color. It can be an indicator of different soil types, and it can indicate certain physical and chemical characteristics of that soil. And due to humus content and the chemical nature of iron compounds in the soil that are present, you can see this chart below, and it can actually dictate just by looking at the color of the soil what you could expect to see in it. Gray soils typically are going to be in anaerobic or areas without oxygen. And what that does is the iron that is in that soil is going to reduce and become gray. And what you can do to test that is you can take a chunk of that soil that's gray and set it out and watch it turn orange over time. And it usually happens fairly quickly as the iron rusts and oxidizes in the presence of air once you get it out of that anaerobic condition. You can also see, looking in soils where plant roots have gone in and carried oxygen, and you'll see orange streaks following the paths that the roots took through the soil as well. Here's just an example of the colors of soil. And we use a Munsell book to help key that out. And Alexander Schmidt did an excellent job with her 2 videos showing some of the how to use the USDA texture triangle, as well as going over the Munsell book. So pay very good and close attention to the videos that she did, because those are excellent resources. Factors that might affect soil structure: the type of clay that we're working with, the amount of organic matter in that soil, any freezing or thawing that we have, wetting or drying, action from burrowing organisms, and then the growth of root systems of plants. Those are all going to affect the structure of the soil. We talked about shrink swell clays earlier when they get wet or dry. We talked about freezing and thawing in a soil that can break up some of the structure. Organic matter is really good for soil structure. Organic matter is like a sponge. It holds on to moisture and it holds on to nutrients very well, and it withstands or helps bind things together and helps kind of withstand some tillage or compaction issues and helps improve soil structure. And then the action of burrowing organisms, worms, beetles, things like groundhogs or prairie dogs also can affect soil structure as well. And then the root systems of plants can affect structure. You can take a compacted soil and try to grow something like tillage radishes, turnips, or beets on it. that have very large, powerful roots that can go down and over time break up these compacted, consolidated soils, and pave a way for you to be able to grow something that requires a soil that has better soil structure and it's not as compacted. So you can use plants to do the work of machinery um, more effectively and cheaper a lot of times. And then the nature of the products of decomposition or organic matter. So that's going to tie into the nature of the microbial population. And organic matter, like I said earlier, is going to be kind of like a glue that helps hold the soil together and helps with aggregate stability, as well as if you have a healthy microbial population, because microbes and plants as well have things called exudates, in which they will exude things in the environment as they begin to break down organic matter and decompose things. And these exudates act like glue, and they help attach the bacteria and other things to the environment in which they are living and consuming. And those exudates just help glue everything together and give you a very nice, stable aggregate that is going to be more resistant to being, if you disturb it, it won't just collapse into a pile of dust. And then bulk density, we determine that by dividing the weight of oven-dried soil in grams by its volume in cubic centimeters. And a variation in bulk density is going to be due largely to the difference in total pore space. So if you have a very well-developed, well-aggregated soil with a healthy microbial population, as well as just a healthy biotic population, you may have some earthworm burrows in there and root channels and stuff that opens up that soil, kind of think like Swiss cheese. That's going to make it very light compared to a soil that may be compacted, that doesn't have good soil biologic activity, not a lot of roots, not a lot of organic matter. That's just super dense and compacted, and it's not going to have a lot of pore space, so it would be a denser soil. So you want soil that is not dense if you're going to do anything plant related or crop related. You want a nice aggregate soil. So the effects of bulk density, engineering properties, water movement, and rooting depth. Engineering properties, you're going to want a soil that has a good bulk density. You want it to be a solid foundation. You don't want a lot of pores and holes in it, because if you go to build a barn or a bridge or something on it, if those pores collapse or something like that happens later on, the foundations could settle and the entire project could collapse. But also water movement. If you have a very dense soil, water may not move easily through it. Whereas if you have a lower bulk density soil, a soil that has a lot of porosity in it, kind of like a sponge, you're going to see water moving through it more freely and being stored in that soil for later use by plants, which is something that you want. And then the rooting depth of plants, if you imagine concrete as being very dense, it would be very difficult for plant roots to penetrate concrete. Whereas if you had something like potting soil, it would be a lot easier for the roots of those plants to penetrate and grow, so they can put more effort and energy into growing the plant and the crop rather than trying to grow their roots. And here's just an example of water movement through starting on the left to the right: granular, prismatic, subangular, blocky, and platy soils. And you can see the granular soils, the water kind of just goes straight down. It doesn't have a lot of stuff interfering with its path. If you look at the prismatic, you can see it going down the water is having to make a few twists and turns to get down through the soil, but still it does look like it's moving pretty easily throughout the profile. Subangular blocky is going to be similar to the granular. You can see it's working its way down. It's having a few more interactions with the soil particles around it, causing it to kind of squiggle around. And then you see the platy, where it's in those really dense layers, and you can see that water is having a really hard time working its way down. Instead of just going straight down, it's having to go left and right and work its way down. So that soil you could assume would not have very good drainage, or it would take a very long time for water to drain through it. And then living systems are occurring both above and below the surface of the soil, and they're determined by the properties of that soil as well. And because we can't see it, and it's very hard to see with the naked eye, we often ignore soil. It's often not as fun as just walking through the woods, looking at all the different trees and the plants and the animals and stuff. With the soil, you really are having to get down in the soil looking, and it can be something that a lot of people just aren't interested in. Um, but soil is the basis of the ecosystem. And soils support all kinds of life. There's bacteria and fungi, protozoa, nematodes, different arthropods, and earthworms that soil life or soil support. And the benefits and roles of these animals, they are good decomposers. They help release nutrients tied up in dead organic matter like plants and animals and help release those nutrients back to be taken up by other plants and animals. They create pores in the soil to let air and water easily infiltrate to get to the roots of the plants, and they help stabilize soils as well with those exudates and things like that. And then here we have a detritus-based food web as well as a plant-based food web. So we see the sun feeding the plants feed the herbivores, and the herbivores feed the carnivores. And then we look below the dotted line for the detritus-based food web, and we see soil organic matter from the plants, from herbivores, waste, manure, them dying, the same from the carnivores, going into soil organic matter. And then a few things can happen with that. Decomposers like bacteria and fungi and microvores like protozoa and nematodes can work on that soil organic matter and eat it to get their nutrients and nutrition. And they then become soil organic matter themselves, as well as predators of these decomposers eating them and becoming soil organic matter themselves. And then over time, you get stabilized organic matter, and that is a heterogeneous pool of slowly decomposable, physically protected compounds. So there's going to be items that are protected deeper in the soil from biologic activity to keep them from being decomposed and degraded. But if you do something like till and you bring that organic matter up to the surface where it has oxygen, where it's easily accessed by other living organisms, then they will eat and burn up, so to speak, that organic matter, and it will be lost, and you'll have to start building it up all over again. And then here we just see soil management affects soil quality and soil health. So if you take care of your soils, happy, healthy soils usually equal happy, healthy producers, a happy, healthy environment. If we just take from our soils and don't give anything back and don't treat them well, if we just kind of use them and abuse them, that soil health and quality is going to go down, and then it's not going to yield as much as it used to. Crop production is going to go down. And as the population of the world exponentially grows, taking care of our soil and soil health is going to be more and more important each year as we are needing to feed more people on less land each year. And then here's just a homeowner soil quality guide. I'll briefly go over some of this material with you all, as well as we can apply it to crop growers as well. So, if you're picking a crop field or you want to grow some crops at your house or in like a small raised bed garden or something, you want to look at the location. Do you have good drainage? Are the slopes steep where you might have a lot of runoff or erosion? Is the soil wet? Do you have a high water table or does it not drain well? Are you in a floodplain that might flood periodically? Is the soil shallow in relationship to maybe like the foundation of a building or some drain fields that you're wanting to put in to maybe help keep water off some fields? And then cooling and heating your home, and then gardens and the landscape. So gardens and the landscape with soil quality, parent material is going to dictate the buffering capacity of your soil. The drainage capacity of your soil is going to control the type of aerobic or anaerobic environment you have. Like we talked about earlier, you could have a gray soil, and then when you introduce it to oxygen, it might oxidize and turn red. So that drainage, if you have aerobic or anaerobic, is going to also impact nutrient availability for certain plants. And then the landscape position is going to dictate where the surface water goes. If you think back to the picture of the soil on 0 to 3% slopes that was periodically ponded, depending on where you want to put your crops or your garden, you might have to deal with periodic ponding if there's not any drainage or the ground doesn't slope away from where you're wanting to do it to help carry water away. You may be in an area where it ponds frequently. Excuse me. So aspect in relation to soil temperature and soil moisture, evapotranspiration, keeping soil covered is going to keep it cooler and help keep moisture in longer for plants. The cooler the soil surface, the better for most plants. So if you keep a field nicely covered with grass or hay pasture, or even the crop that you're trying to grow, just to get it to grow as fast as you can, to cover up that soil and protect it like an umbrella, your soil won't dry out as quickly and it won't get as hot. And shaded soil can be several degrees cooler than unshaded soil, which can impact both the plant health of the crop you're trying to grow as well as the animal life in the soil. So if you make it more suitable for the beneficial organisms to grow and flourish, that will also benefit your crop and plants as well. And then inherent available water capacity of soils and how they can be altered by management. And then inherent organic matter content, aggradations, degradation, and maintenance. So adding organic matter, trying not to degrade organic matter, and then trying to maintain a good level of organic matter in your soil. And then the original vegetative state of the garden, and then the original soil biota of the garden or field. Here are some links. You can click on all of these little hot links here, like agronomy, cropland, organic agriculture, stuff like that. It will take you to some different websites that will help you with soil quality garden landscapes. But things that you want to try to do in any cropping situation is enhance your organic matter. You want to avoid excess tillage because, like we said, that'll bring organic matter to the surface and it'll be broken down by bacteria and other things in the soil, causing you to lose it. Managing pests and nutrients efficiently, like soil testing to know how much nutrients you need to add to your soil for the given crop you're trying to grow. Prevent soil compaction, so try not to tread on the soil when it's wet and it's easily compacted. Keeping the ground covered, either with living matter, plants, or some type of thatch layer, cover crop, stubble, something like that, just to keep the soil protected. And then diversifying your cropping systems just by trying to rotate crops around. Because if you grow, say, tomatoes in the same spot year after year, tomatoes are susceptible to several types of blight and fungi and bacteria. And if you grow them there year after year, the soil gets laden with those spores and bacteria, and they'll be there for next year. And when you plant your tomatoes, they're just going to get reinfected. But if you plant something that those bacteria and fungi don't bother, like corn, in that spot, then you break that cycle. If you plant something else there for a couple of years and then come back with tomatoes, the bacteria and fungi count in the soil is not going to be as high, so your crop is going to do better. And then here's just some additional information on soil health management on a website that you guys can go to get some additional information. And here's another one that you can go to unlock the secrets in soil. Here's just a little poster that we have on unlocking the secrets of soil and kind of some nice facts about what soil does for us, the amount of water that it can hold, how much organic matter increases, water retention, things like that. And then we've got urban soil primer, and I'm just going to kind of go over this part rather quickly for you all. We have topsoil and subsoil. Topsoil is going to be high in organic matter, low in salts, and high in natural nutrient levels. And then subsoil is going to be lower in your organic matter, high in salts, low in nutrients, and higher in clay and lime. And then we kind of break soils up, like we talked about earlier, into horizons. So we've got an A horizon here. It's going to be about from here to here. And then we've got an E horizon from here to here, a B horizon from here to here, and a C horizon from here to here. And that's going to just kind of show you guys a little synopsis on the horizons. And as urban development continues, locating good quality topsoil becomes more and more difficult, and the price is going to increase as a result due to supply and demand. So the availability and the price may also mean that marginal topsoils are used in certain landscapes, so it may not be the best soil. So if you have to get a marginal topsoil, then you may have to amend it. You may have to add some organic matter. You may have to, it may have a few extra salts in it, and you may have to add nutrients to it to get it up to an appropriate cropping level. This is a hard to see picture, so we'll skip it. Principles of construction with erosion control. Prevention of urban erosion is best, and here are some basic principles on how to control erosion on like a construction site. The same can be applied to most farms. I'll let you guys read over these if you want to pause the video, and I'm going to skip on. And then examples of the factors that may affect productivity in urban soil: little or no addition of organic matter. A lot of times in urban areas, pavement and asphalt are all we see around these little green specks that we have. So there's not going to be a lot of addition of organic matter like we see in a natural forest with leaves and stuff cycling through. A lot of times in these urban areas, also people rake their yards, get rid of the leaves, get rid of the grass clippings, and send them to a recycling center to be turned into mulch, or to go to a landfill, or they burn them, or just throw them over a hillside. So we're losing that organic matter in the soil, and we're not putting anything back. Artifacts that disrupt water movement, that could be anything like old sidewalks, old cobblestone roads, anything that might impact how water moves through the soil or gets to the soil. Elevated salt content, that could be something from like salt trucks in the winter, treating roads, things like that would add excess salts to the road, or to the soil, excuse me. And then interrupted nutrient cycling and modified activity of microorganisms. You could kind of tie that to the little or no additional organic matter, in which people are removing a lot of the organic matter, a lot of the nutrients and grass clippings and stuff like that from the soil, so you're not going to get good nutrient cycling there. And then without the additions of a lot of organic matter in those soils, you're going to affect what organisms live there or can live there. And then higher soil temperatures, that would be like you get the urban heat island effect. A lot of cities are going to be warmer, especially down towards the ground level. And those higher temperatures are going to increase the rate of chemical reactions. So the warmer it is, the faster certain reactions are going to take place. So if you have certain things in the soil that you want to keep there, that when you have a cooler soil, allows those to stay more stable, and you increase the heat, then you may be losing some of those fertilizers or things like that, particularly nitrogen. And then you're going to have generally higher pH values, and that's going to be as a result of a lot of plaster, road salts, and then just cement. Concrete is everywhere in cities, so that's going to alter your pH with the water flowing over top of that to get into these areas. And then we've got the sideways subsurface water flow, and that's going to be as a result of compacted layers. So it's going to be harder for water to go straight down, so it's going to move laterally or sideways through the horizons. And I'll just let you guys read over this little bit on organic matter and how it is like a sponge and helps bind chemicals and nutrients together, kind of like clay. And just a description of how organic matter is a dark surface layer. So I will skip on. Here's just an example of cooperative extension. They're a great resource to contact. You can talk to the extension agents for each county, or go online to Virginia Cooperative Extension. It's through Virginia Tech. This is just an example of some of the cards that we use or they use to go through and assess different sites for different capabilities. Here is another website with NRCS to go to get some different information on what we do, or different tools that you guys can access for different information. And I'll just kind of skip through these. Here's a Virginia Cooperative Extension website link on how to control erosion in your own backyard, managing compacted and heavy soils, how to do soil samples, things like that. And then I like this chart. I wanted to share this with you all. It's crop responses to fertilizer application. A lot of times people think that the more fertilizer you put down, the more better crop harvest you're going to get. But if you look at this chart here, the maximum efficiency of plant use to maximum yield is going to occur about where B is. Anything after B is a waste of money, because you can see C here. You're applying X number of fertilizer units, and you're still getting, you're still getting the same yield as B. So this, from C on, you're not getting any extra use of those fertilizers that you're putting down. They're going to waste. The plants cannot physically use them. So they're either going to just sit in the soil, or they're going to be lost through erosion, translocation, other methods of loss and things like that. And then you can actually see here at D, you're applying a lot more fertilizer, and your plant yield is actually going down, because in some cases, or many cases, too much fertilizer will actually burn up your plants, or you just create a very salty soil, and the plants cannot survive that. So you do more harm than good. So always soil test to know what is in your soil, and you can, on the soil test, mark what crop you want to grow. And we have a good understanding of what each plant needs to grow, its nutrient requirements. So we can come up with some very good estimates on how much of each, like NPK, nitrogen, potassium, phosphorus, that you need to add to your soil to get a good harvest without adding too much or too little, because fertilizer is expensive. And then here's just some additional information from Virginia Cooperative Extension. You can go to this website and get this document here that will tell you all about liming organic matter, fertilizing for different crops and things like that. And then here's another link to Virginia Tech Extension. And that's all. Again, Janine has retired. This was her presentation. I just borrowed it. Again, my name is Emerson Kirby, and you can contact me at emerson.kirby@usda.gov, or you can get in contact with someone from the Clinch Valley Soil and Water Conservation District. That is the conservation district that I work with here in Lebanon, and they can put you in contact with me, and I will be happy to answer any questions you all may have, or try to provide some additional information. And if I can't, I'll do my best to find somebody who can. Stay safe, good luck, and have a great year. Thanks, guys.